Hello guys, good morning. We will be continuing our discussion on tensorial operations. And this time we make use of a generalized case of tensorial product of vectors and matrices. Okay, so for this particular case wherein a tensor product of two vectors are presented, okay, the resulting uh, quantity is actually referred to as a diet. Okay, so we now encounter another term which is a more general case upon which these operations for vectors and tensors are formed and patterned into. Okay, so a diet is simply a quantity wherein uh, the two vectors uh, are placed in what you call a juxtaposition, okay, without due regard to the uh, particular operation you wanted to place into the expression that you are presenting. Okay, so this is a general case. It's called a tensor product in general. Okay, hence if we have two vectors uv, all we have to do is to place it side by side, okay, defining the initial notations upon which okay, your vectors uh, are derived. Okay, so it's called a tensor product of two vectors because our resulting uh, product is no longer a vector. So it is a general case of a tensor. Okay, so it is 1 degree higher than a vector. So in this case, we have two directional description of such a tensor. And in using the procedures or the rules upon which the order of the tensor is made, we can simply verify it on the number again of free indices. So if this is an ij free index, so this is an order of 2. Okay, so if we would like to get the number of components for a three-dimensional uh, range, okay, so we can therefore say that this is a second order tensor. Okay, so the number of components will be something like 9 components. Okay, but as I've said, since it's a general case, when we sum this case, this resulting tensorial quantity, the mere fact that this is an I, and a JJ, okay, so we can say that this is only a scalar quantity. So the interpretation of this can now be represented by a simple summation on I and J, okay, which yields first with the iteration on i's in this form. Okay, so this is a simple I1, I is equal to 1, I equals to 2, and I equals to 3. Okay, and in this scenario, in this particular uh, expansion, we are now dealing with each and every expression here upon which the J range will now be iterated. Okay, so if we do the iterations on J equals 1, 2, and 3, so these are the J's. Okay, so this will represent now your J equals 1. This line here will represent J equals 2. And this line here will represent J equals 3. Okay, so the mere fact that we did not use the, the rule on how to define the components and the number of terms in terms of the vectorial procedures we have on the previous lecture, we can now say that in this particular interpretation of a tensor product of two vectors, the resulting term will no longer be a scalar, but rather it is called a dyad. Okay, so a dyad is simply a 9-term sum, which is also called the nonion form. Okay, so it's a nonion form of the dyad. So nonion means it has 9 components, but they are made to be a single component because of the sum. Of course, when you do the summation, you cannot easily make it, consider it as a scalar quantity since the directional vectors are different from each other. Okay, so they are defined in terms of directional basis vectors. But if you look on the context of ignoring the directions, then you can say that this is now a scalar, but that's not the case. So in general, the product, the tensorial product of two vectors is not scalar, and it's not also a tensor of second order. Rather, it is called a dyad. But if we interpret it within the rules, within the bounds of which your vectorial, okay, operations are defined, then we can now go back to the previous discussion to interpret it as either a scalar or a vector. Okay, so this is now a general case without consideration of the vectorial rules we have considered a while ago. So this is written an alternative notation may be done by using this cross with the circle form. U crossing V is simply equal to UI EI cross VJ EJ, okay, is equal to UI VJ EI cross EJ. So this is different from a cross product of vectors, no? Cross product of vectors. So this is not the same, not the same. Okay, this is not the same as this one here. Okay, so you can make use of this alternative form, or you can use a simple placement of the vectors side by side, or what you call the placement in juxtaposition. Okay, so some of dyads now are called dyadics. Okay, so if you want to look further into this, the diagonal, okay, so this diagonal term here, we will look this term here, so you call this a dyadic. So u1 v1, u2 v2, un vn without due regard course, for the direction of this, because in the vectorial quantity, what is E1 dot E1 is only 1, no? So if you will interpret it now, the adics are simply the same as a dot product, okay? It's actually the same, but it can be interpreted into this form. Okay, so if we set another rule to satisfy our objective of presenting a certain expression or a group of expression, then we just define it. And this is the definition of what dyads and dyadics in continuum mechanics is, as far as those literatures written in engineering is concerned. Okay, so let's proceed with the application of tensorial operation or dyadic operation by simply looking at this. For example, here we have a vector and a dyad. So this is now a dyad versus a vector. Okay, so this is now a vector versus a dyad. So we take a look at that a tensorial operation forming a dyad now is actually being made to be operated with another vector by means of a dot product or a special tensorial operation. Okay, so we are now mixing it up. This is a cross product of a dyad and a vector. Okay, it's still, we have a dyad here. This is not a tensor. Sorry, this is not a matrix in general. It's a, uh, a, a tensorial quantity which is specifically known as a dyad. So this is now a vector again crossed with a dyad here. Okay, and look at the operation after which you have grouped and expanded it in initial form. All you have to do is to take note of where the dot product is and look at the directional vectors. EI and EJ now becomes what? Okay, so when you dot an EI dotted to EJ according to our elementary operation, what is this? This is simply a delta ij. Okay, so delta ij will now be what? Interfering with one of the vectors here inside. Okay, so you cannot you don't touch a UI. What you touch here or you try to consider here is the VJ. So when I multiply the VJ here, because I have now an EI dotted to EJ, which is delta IJ, the nearest vector is VJ, therefore I can make use of contraction, no? So if I have a delta IJ and then I have a VJ placed on the side of it, then I contract this, I can have now a VI. Okay, so that's why there's a VI now here. I place UI there as is and place WK here, and I retain my EK. So what is this value here now? This is a simple vector. So the resulting quantity upon which a vector and a dyad is multiplied will result into a vector. Same is true with this case. Why? Because you just interchange the position. So if I just interchange the position, what will be multiplied here is the EJEK forming a delta IJ there. Delta JK. Okay, so a delta JK, and the nearest to the JK here is the WK. So I will now contract K and K, so I have a WJ there. And I retain UI VJ, and then this is the EI that is actually present sorry, here in the direction of ui. So this is again a vector. Okay. How about the third one? So we have a cross product of a vector and a diet, and a cross product of the diet and the vector should just interchange the position. And we take note that again, crossing uh, an EI with a V with a VJ here. Okay, an EI cross to VJ is simply, sorry, an EI cross to EJ is simply a permutation, which is a permutation of EIJ. Okay, whatever is the uh, uh, subscript you want to place here. So at this point in time, I use a Q here. So it's an epsilon ijk Q of what? Okay, of an EQ. Okay, so whatever is the subscript, last subscript there will yield the subscript of the directional vector. That's why you have a period and epsilon IQ and then an EQ there. And then you just place side by side the remaining quantities UI, VJ, and WK. And so is true with this number 4 problem. No? So just associate now the cross product of V and W here by these two. So it's now epsilon JK Q. So we have an epsilon JK Q, and then you just write the quantities UI, VJ, and WK before writing. Okay, so we cannot no longer collapse this because this is the last thing you can have with these direction vectors. There's no other special operation situated in between the two. So it's not a cross, it's not a dot. So we just place it side by side, referring to both directions as a basis for your computation. So whatever is your interpretation of what EQ and EK is, EI and EQ is, then you will proceed uh, accordingly as the problem dictates. And if you look into this expression now, this is simply what? Epsilon ijk, that's an ij, so you have actually only one free subscript. If you will look into or free index, you will look into this scenario. No? So we have one index k, and of course you consider now your q as also one another index to represent now a tensor of order. So this is a tensor. If you are looking into the order of the tensor, this is a tensor of order 2. Okay? But again, you cannot call this a tensor because as defined here, a UV with two directions, okay, is simply referred to as a diet. So your resulting value here, vector, but here, the more appropriate term is that this is a diet. So is true with this one. Okay, so note that E in 3 and 4, the order of the base vector, EI is very important because it will define whatever range, no? Range of of course, index or subscript your diode will have. No? So if it is a third, a three-dimensional vector or position or direction in space, then you have a non-ion form of this diode. So you have this form uh, in terms of the expanded notation. Okay? So for the diode product, dot product, okay, so this is now a dot product of two diodes as placed here. So take note of the association of the near or the inner values of the of the variable representing the diode, and that's VW. So this must be VW dot. Okay, so these are the ones you have to contract. EJ dot EK now becomes delta JK. Okay, so this delta JK now is near, no? Is both near to VJ and WK. So you can actually make a contraction either on VJ and WK. So this time it was chosen to have contracted delta JK to the WK there, therefore this becomes a WJ. So you can also make the other way around, but since these are dummy index, uh, it doesn't change anything. No? Okay, so this is now a VJ, WJ, or a VK, WK. So it does not change anything because it does not interfere with the other subscript of the resulting expression. Then you just place U at the side there and S at the other side, okay, with the same subscript as is. Then of course your EI depth and EQ as is. So you can no longer dot this because the dot operation was also already used by this one. So some books may be presenting a double dot product, triple dot product. So they're just defining those special details of the operation to satisfy their objective in a particular problem. So since we are just here to do some mathematical understanding, we don't go very deep on that level yet. Okay? So this is a UIVJ, WJSQEI again. This, if you look at the rule for subscript, may be considered as a second order tensor, but specifically this is a, the description as defined above regarding diodes and pleiadics. Okay, for letter I, vector and tensor product, you just do the same. Of course, if this is already a tensor, then your subscript must be a JK. No? Free index must be 2. Okay, so TJK, EJ, EK. So when you define now a tensor in only one variable, so any tensor in only one variable must have two index. Let's say RS, TRS. Okay, but you have to place automatically the directional vectors in juxtaposition like this. Okay, so ER and ES. This is also the form TJK, EJ, EK. And then there's a dot there, so the nearest, okay, the nearest directional vector is EI and EJ in between or connected by the dot product there. Therefore, this becomes a delta IJ, and this delta IJ will contract with what? With the VI there. Okay, it's near the VI, or you can place it on the TJK here if you want. But here it was placed on the VI. Okay, that's why sorry, it was placed on the tjk, so that this is tik now, no? So vi was retained. Vi there, yes, this the t, this is now the contraction on j, so this is now a tki. A tki and a tik, uh, in this particular case, are the same, although in some cases the tik and the tki subscript means a different thing. Okay, so it can mean a transpose of a matrix, but if for symmetrical matrices it does not uh, create any trouble, no, with regards to tensorial multiplication. Okay, particularly matrix multiplication in that regard. So this is now a VITIK, and take note that you have only one direction here, which is EK. Therefore, um, as you can see, VI and TI can now contract, and you can form a more specific. Let's say VT is equivalent to S. So this is SK EK. Okay, but the final answer here is like this, so we just leave it like this, and the resulting form of this is a vector. Okay, so this is a vector, and if you reverse the situation, you will get the same, almost the same answer, but only the Tij here was at the first, no, written at the first prior to the second term here. Okay, so this again can be replaced by an Si EI. Okay, so again, this is now the resulting quantity is a vector. Note that these products are also written in terms of the form Vt and Tv. Doesn't matter in a vectorial representation. While a tensor product will yield to a tensor. Okay, so this is now a tensor, or simply again, in general, a diode. Okay, so, but if you look and consider special cases, you can regard this as a second rank tensor or second order tensor. So that's it for uh, the rest of the operations. I want to discuss you the example 2.2-2 next in the next video, because this will give you an understanding on the E delta identity I was talking about on my previous lectures. Have a nice day, and thank you for listening.